All right, up next in our industry update, we have Brian Cooke, Technical Manager from Clariant out of Sellersburg, Indiana. He's going to report on the adsorptive removal of contaminants from fats and oils for production of biofuels. And Brian, if you want to take it away, first tell us a little bit about yourself and before we hear your presentation.
Hello, everybody. Manager for North America, and I have the pleasure to talk to you about the removal of contaminants from fats and oils that are used to produce biofuels. To get started, we'll start with a brief introduction, look at the adsorption process, and talk a little bit about bleaching clay characteristics. We'll then move in and talk about both biodiesel and renewable diesel production and how those contaminants that are present in the fats and oils need to be removed for those processes. And we'll end with a brief summary. So as an introduction, both biodiesel and renewable diesels are both derived from fats and oils. The biodiesel, the difference between the two, biodiesel is a methyl ester. We'll go into a little bit more detail on what that entails. Whereas renewable diesel converts those fats and oils directly to hydrocarbons, very similar to petroleum-based diesels. Some of the problems that arise from the fats and oils is they can contain contaminants, which can interfere with the reaction in biodiesel and also decrease the catalyst for the renewable diesel process. For biodiesel, we're going to look at the pretreatment of the fat and oil to remove contaminants in the feedstock, as well as after the reaction is completed, there are some contaminants that still need to be removed before that product is actually biodiesel. For renewable diesel, we're mainly concerned with the pretreatment, trying to remove those contaminants as much as possible up front to protect the catalyst and help the life of that catalyst. So just as a basic introduction, we have saturated fatty acids and unsaturated fatty acids are connected to a glycerol backbone. That's what makes up the triglyceride. Saturated fatty acids are more stable. They're less prone to undergo oxidation, but especially for biodiesel, they cause cold flow issues at the end of the process. Unsaturated fatty acids are less stable, and they're more prone to undergo oxidation, which is more important for biodiesel because biodiesel converts those fatty acids into methyl esters, and so you still have those fatty acid molecules there that can undergo oxidation, whereas with renewable diesel, those are converted to hydrocarbons and you don't have the oxidation issues. So now we're going to talk about the adsorption of contaminants and a little bit about bleaching clays. To start with here, we need to understand the difference between absorption and adsorption. Absorption is just the accumulation of the liquid within a solution, whereas adsorption, you're actually selectively removing contaminants. So the best example I can think of is if you had a solution of water with sodium hydroxide that is totally dissolved, you put a sponge in, that sponge is going to soak up both the sodium hydroxide and the water. Whereas with adsorption, if you had that same situation and you took that sponge and squeezed it and just the water came out and the sodium hydroxide was held onto the sponge, then we're talking about an adsorption phenomenon. So when we're talking about the adsorption filtration process, we're going to be removing those soluble impurities. It's also going to provide depth filtration. As you build up the material in the filter cake, you're going to remove down to 1 micron or less. So you're going to result in a higher quality feedstock for both biodiesel or renewable diesel. You're going to help achieve regulatory specifications by removing those metals and contaminants up front. That'll help with the reaction as well. So reaction efficiency is going to be improved. And on renewable diesel, you're going to increase the life of the catalyst. Just very briefly, we're going to look at the origin of bentonite. Clariant produces bentonite products as bleaching clays. So years ago, volcanoes shot up lava that had gas and ash. Sometimes that traveled as much as 16 miles. The ash, as it falls, it gets carried away by the wind and water. And over time, those deposits are subjected to high pressure, temperatures, and they form bentonite. So the landscape undergoes massive changes, and what's left behind is the calcium bentonite products that are then processed to make bleaching clays. One of the things we want to look at is if you just dug the clay out of the ground and processed that as is, you're going to look at a surface area of about 60 square meters per gram and a bulk density of about 800 grams per liter. To increase that surface area and really give it a boost to remove those contaminants, that clay is subjected to acid with temperature, pressure, and time to form what we call a acid activated bleaching earth. So that's going to increase the surface area to about 200 square meters per gram or a little higher, and also reduce the bulk density. These products have been used for many years in the edible oil and mineral oil industries, and also in biofuels as well, as we're talking about today. So take a closer look at the biodiesel production. I'm not going to go into a lot of detail on the reaction, but basically you start with the triglyceride. So if you had 100 kilograms, you would react that with 10 kilograms of methanol in the presence of a catalyst to form 100 kilograms of fatty acid methyl esters and 10 kilograms of glycerin. So during this reaction, we do have glycerin as a byproduct that needs to be taken care of, whether that's sold or used for a different application. If we look closer at the process, so you start with the fat or oil that gets reacted with methanol, and you form biodiesel at the end of the process. But there's a lot of nuances to consider as you go through this reaction process. The first part of this is the pretreatment. So you want to take your fat and oil and remove as much contaminants from that as possible. You'll have metals, you may have soap, you may have some residual free fatty acid that needs to be removed, but that should be taken care of in the pretreatment process. And then another thing to keep in mind is if you have an FFA greater than 2%, you really want to consider doing a direct esterification process where you directly convert those free fatty acids into methyl esters. If you didn't do that process and you went straight to the trans-esterification reaction with the sodium hydroxide catalyst, then you would form a lot of soap that would create a lot of emulsion, and it'd be very difficult to separate. So for that direct esterification process, an acid is used for the catalyst to convert that. So at the end of this process, we end up with contaminated methyl esters after the glycerol is separated. You're going to have some residual glycerin. You may have some metals that made it through that need to be removed at the tail end of the process. So you have a post processing step that you have to do, whether that's just a water wash with distillation. But typically after that, you still want to do a final polish to make sure the biodiesel meets the specifications and that all the contaminants are removed. So that's where another place where the use of an adsorbent can come into play. So as we look a little bit more detail on some of the contaminants that need to be removed, the left side of this page shows soap removal. So this particular feedstock had about 500 parts per million soap. That was treated and filtered with 0.2% bleaching clay, able to take that down to about 150 parts per million. But in order to remove all that soap that was in there, a 0.5% by weight, bleaching clay was able to achieve 100% removal of the soap. Phosphorus is another contaminant that really can interfere with the reaction in biodiesel. You can see the oil feedstock started with about 20 parts per million. And again, that same trend, we used 0.2%. That took it down to about 12 parts per million. But in order to get that down to levels below detection, a 0.5% by weight bleaching clay was used. And it's important to get that phosphorus down as low as possible, preferably less than 2 parts per million for the reaction process. When we're looking at the post-reaction process, as I said, the glycerin gets separated from the fatty acid methyl esters. At this point, you have contaminated fatty acid methyl esters. They're not biodiesel until they meet the specifications. And so some of the contaminants that need to be removed include some residual glycerin, soaps, some metals, and excess methanol or catalyst that made it through the reaction. So looking at the post-reaction, some of the things to keep in mind: soap formation, that results again from the alkaline catalyst reaction with the free fatty acid. If you had oleic acid, for example, that would form sodium oleate. So that can come from high FFA feedstocks, excess water in the reaction. You want to keep that reaction as dry as possible because you can get direct saponification of the triglycerides if you have enough water in the system. It could also indicate an improper amount of catalyst. That can cause emulsion problems, and so when you go to separate the glycerin from the methyl esters, you're going to have some issues trying to do that. Soap is going to require more adsorbent. The more soap you have, the more adsorbent you're going to need. Looking at some other things, insufficient catalyst removal that can cause injector deposits, filter plugging in the engine. Poor glycerin separation, that can cause reversion, make the reaction go backwards, so you can actually start to form monodi and triglycerides. If you have a high acid value, that can decrease the shelf life. It can lead to oxidation. Those acidic molecules can really act as a catalyst to further oxidize the product. Insufficient alcohol removal, there's a safety concern there, of course, but that can cause premature injector failures in the engine. So it's important to make sure all of these contaminants are removed, not only up front, but at the final polish for the biodiesel production process. Looking at some other things to keep in mind, you may have some hazy precipitates that are found in the finished product. Those could be sterile glucosides, maybe some saturated monoglycerides. So those need to be removed as well during this process. And the good thing about using an adsorbent to remove the other contaminants is they will remove these sterile glucosides as well at higher temperatures. So you don't have to cool the biodiesel down to actually precipitate those products out. You can do that at temperature and they'll be removed as well. So now we're going to talk about renewable diesel and what contaminants are present and why they need to be removed from the process. So renewable diesel is a true hydrocarbon, just like petroleum diesel. It meets the ASTM specifications for diesel fuels. It has a different structure than biodiesel, which we've talked about. Biodiesel has that methyl ester structure, so you have to worry about oxidation, not so much for renewable diesel. So for the renewable diesel, you're hydrotreating the product with a catalyst, which is a highly active catalyst that's used to remove the oxygen and nitrogen and produce the diesel fuel for production. The pretreatment is essential for this process because that catalyst is very expensive, and especially contaminants such as phosphorus really need to be removed because that can really poison the life of the catalyst and cause a significant investment, premature disposal of the catalyst. So when we're looking at bleaching clay and renewable diesel process, look at the process here. You start with the fat or oil. You go through the pretreatment process to remove the phosphorus and other metals, because other metals can interfere with the catalyst also, but phosphorus is the most problematic. That then goes through the hydrotreating reactor with the catalyst to produce your renewable diesel, which is sometimes called green diesel, and you have propane as a byproduct, which can be reused in the process. So here we're going to focus on the pre-treatment process for this reaction. I'm not going to go into all the detail on the chemical reaction that takes place to form the hydrocarbons, but it's basically a decarboxylation of the organic molecules followed by a isomerization step to produce the petroleum-based, or the renewable diesel at the end of the process, as well as propane and some naphtha as a byproduct as well. So during the reaction, the catalyst is required to conduct these reactions, and as we've talked about before, the life of that catalyst is important because it's a very expensive catalyst. So as I've talked about a little bit, the catalyst poisoning is mainly by the phosphatide compounds. These are some examples of phosphatides here on the right. I'm not going to go into detail on each one of them, but there are some that are most prevalent, like lecithin. You might be familiar with that, but these compounds contain phosphorus, which can poison the catalyst and decrease the life of the catalyst. The origin of phospholipids, so a simplified drawing, you see it has a nonpolar tail and a polar head. They tend to form micelles. So a large amount of the phospholipids come from cell membranes, and again, they migrate together to form micelles. So a lot of these can be removed by the acid-water degumming process to remove the hydratable phospholipids, but the non-hydratable phospholipids will remain behind with the oil, and those are the ones that need to be removed with an adsorbent. So looking at the non-hydratable phospholipids, they're often stabilized with calcium or magnesium. You can see the process here on the left. You have the phospholipids interacting with the acid clay. They get bound to the clay surface, and then they're filtered out so they never reach the catalyst and damage the catalyst. The right side of the table here, you're just looking at the adsorbent dosage is going to be proportional to the phosphorus concentration. So, I mean, if you have something that has 340 parts per million phosphorus, you're going to be using a lot more adsorbent than you would with something using 100 parts per million phosphorus. So here is kind of a diagram showing this is the filter cake that's formed on the filter with the bleaching clay. There's your catalyst. You have your oil with the phosphorus going through, hitting the catalyst, and you see the phosphorus is left behind on the filter cake, so it never reaches the catalyst. On the right there is just kind of a picture of what this isolated phospholipid material looks like when it's trapped on the filter cake. So the next couple of slides, we're going to look at some examples. We started with a yellow grease. The phosphorus was 85 parts per million. That went through an acid degumming and water wash to remove that down to about 19 parts per million. After the use of 1% by weight clay, that was reduced down to 1.5 parts per million, down to less than that 2 parts per million as we talked about before. So the life of that catalyst is really going to be extended by removing all that phosphorus. And you can see a significant amount of it came out with the acid degumming and water wash process, but there's still a significant portion that needs to be removed with the adsorbent process. Again, here's another example. This particular example, you're looking at some high performance bleaching earth. So they're using a lot more acid and temperature and pressure to really increase that surface area. And you can see it took about a 0.75% by weight treatment to remove that phosphorus that started at 20 parts per million down to less than 1 part per million. And then you also had a total metal removal of 91%. So you're really protecting that catalyst and preventing those contaminants from hitting that catalyst. Looking at filterability, that's another important aspect. We're able to control the porosity and the particle size. So looking at this table, you can see the x-axis shows the time it took to filter, and the y-axis shows how much oil was filtered in that time. So Adsorbent A was able to filter 300 grams of oil in about 80 seconds, whereas B and C took 200 and 300 seconds to filter that same oil. So filterability is another important aspect. Since you're doing a filtration process, you want to have high throughput as well as contaminant removal. So to summarize, adsorbents are processing aids that can help prevent the contaminants, both for the biodiesel process as well as the renewable diesel process. The activation of those clays is done through the use of an acid with temperature and pressure. Porosity and particle size are controlled so that you have better filterability, better flow. The better flow you have, the more you can process and the less you'll have to clean out the filter. The adsorbents can also be used as a final polish for biodiesel to help achieve regulatory specifications. And the use of the catalyst or the adsorbent can really help increase the life of the catalyst and help significantly with the cost associated with the renewable diesel production process. So I'd like to thank you for your attention, and I'll be more than glad to answer any questions when we have the question and answer session later on. Thank you again.
Thanks a lot, Brian. First, I want to apologize for the technical glitch that I caused. I did not give Brian the proper introduction. I'm going to do that post-presentation and before our questions here. Brian is the technical manager for Clariant in North America, in case you didn't gather that already. He's in functional minerals, involved with oleochemical applications for over 25 years. A degree in chemistry from Indiana University. Before Clariant, he spent his career at the Dallas Group in dieselite minerals. He's given numerous lectures regarding filtration and absorption during industry events like AOCS, Eurofeed Lipid, and other industrial short courses. Now we'll go into a couple questions here. Brian, what are the oil losses associated with the clay filter cake, and why should BD and RD producers choose ABE versus other synthetic adsorbents?
So typically with bleaching clays, it's about 25 to 40% by weight of the clay is going to be the oil retention inside, and that's going to depend on a lot of factors. The main factor that's going to depend on is the porosity of the particles. And with our products, the way they're produced, we're able to control that porosity till we have a large porosity, which decreases the amount of oil retention. So it's more on the line of the 25 to 30% by weight of the clay being used. And what was the second part of that question?
Why should producers choose ABE versus other synthetic adsorbents?
So there's a lot of factors that go into looking at the overall quality of the oil going into the process. So number one, you want to concentrate on products that work, that you know work, and they've been used for many years to remove the phosphorus and metals from the oils. And then you also want to take a look at the total cost of ownership. So if you're looking at a synthetic product, you're going to have a significantly higher cost associated with that. And those products typically won't filter as well and have a little bit higher oil retention. So when you put all those pieces together, the activated bleaching earth is a much lower total cost of ownership for the process.
Okay. Could you comment on the parameters influencing expected useful life and disposal of the product?
So the useful life of the clays. So I mean, basically what we're talking about there is the higher the amount of contaminants you have in the raw material or the feedstock coming in, the more adsorbent it's going to require. Typically, you can see up to a few hundred parts per million of phosphorus coming in, but a lot of that's removed during the acid water degumming process, and so you're left after that process with something around 15 to 30 parts per million phosphorus, and that's going to take about a half to 1% by weight of bleaching clay to remove that phosphorus from the feedstock. Once that clay has been used, it has to be it's a one-time use. You can't really reuse it. Once it's absorbed what it's going to absorb, you can't really get any more activity out of it. So disposal is something we're always looking at. With renewable diesel, it's a bit difficult because of the feedstocks we're dealing with, animal fats and yellow grease, used cooking oils. Whereas with edible oils, some of that filter cake can be actually added to animal feed. That's not the case for the renewable diesel industry. So it's something that we're aware of, and we're looking at ways to mitigate the losses associated with having to dispose that material.
So renewable diesel versus biodiesel is a good lead in here. On average, how much more adsorbent is used in renewable diesel than in biodiesel?
It's pretty close to being equivalent. Again, that's going to depend on the feedstock. If you're a biodiesel producer that crushes your own soybean oil seed, then typically you're going to process that oil anyway with a bleaching clay to remove the phosphorus and the chlorophyll, which is not important for that process. But those contaminants are typically removed prior to going into the process. But if you're a renewable diesel processor that is purchasing yellow grease or a used cooking oil or an animal fat, then you have to make sure you have that pre-treatment process in place for your setup for your renewable diesel plant.
Okay. What is the typical loss of oil to the bleaching clay, and what happens to leftover bleaching clay?
That's what we just talked about. The typical losses are about 25 to 40% range. And again, for the renewable diesel, just because of the nature of the feedstocks, the spent filter cake is being landfilled right now. But that's something that we are actively looking at different ways to mitigate those losses associated with that.
Okay. Do any metals leach out of the clay?
There's no metals that are going to leach out of the clay. It's processed in a way to where those uh, it's acid activated, but the acid is washed back out. And the only purpose of the acid is really to increase the surface area and increase the ability to actually remove the metals from the feedstock.
Okay. And it looks like a last question. How does high FFA in the feedstock affect the absorption capacity of ABE?
That's not going to have an effect on the absorption capacity. We're talking about metal removal. The activated clays typically are not going to remove FFA anyway, so that is not going to interfere with the other contaminants that need to be removed.
Okay. Looks like that is all our questions. Thanks a lot, Brian, for your presentation. Very interesting. Appreciate it.
All right, thank you, Ryan.